Yeah, good morning my dear students. Today I am going to discuss in detail about the various IR spectrometric detectors along with the sample handling procedure in IR spectroscopy. So as a part of that, the first important detector what we are going to discuss is thermocouples. The thermocouples are also called as thermopiles. What is the meaning of thermocouple? Thermocouple is the junction between two different electrical conductors, EC1, EC2. This junction is called thermocouple. The electrons have the lower free energy in one conductor. Basically, the electrons have lower free energy in one conductor than in the other, which leads to the flow of electrons from one to the another, until the resulting small voltage difference prevents the further flow. The junction potential is temperature dependent. So, one junction is hotter and the other junction is colder. The junction potential is temperature dependent because the electrons can flow back to higher energy conductor at high temperature. So this is the way the thermocouple is basically working in IR detector. The sensitivity of 6 volts per watt of radiation is observed. Basically the detector response is slow as compared with other detector, and this is the most commonly used IR detector as such. Now the second important detector what we are using is pyroelectric detectors. The pyroelectric detectors are very important detectors, particularly we are using in FTIR spectrometer. This is one of the very important detector in modern instruments also. This pyroelectric detector is basically made up of ferroelectric material such as deuterated triglycine sulfate. We simply call it as DTGS, or sometimes we can use lithium tantalate, or sometimes we can use strontium barium niobate. Any one of the material we are using as a pyroelectric detector. So what is the capacity or what is the characteristics of this material? Basically these are the ferroelectric materials having a permanent electric polarization, because the alignment of molecules in a crystal, right, is in the absence of external field. Without having any external magnetic field or any field, they have, these materials are having the permanent electric polarization, right? So for example, if you look at this diagram, I have shown the crystal. The crystal is having one face as positive and the opposite face as negative charged, right? So whenever the IR radiation, so these absorbed, when the IR radiation is absorbed by the crystal, right? So what will happen? You will see that one face is positive and the one face is negative. The polarization is temperature dependent, and its change with the temperature is called pyroelectric effect. Basically the polarization is temperature dependent phenomena, and its change with the temperature is called pyroelectric effect. The temperature, in the sense the IR radiation is absorbed by the crystal, therefore the temperature of the crystal also gets raised, right? And that is the pyroelectric effect. So its temperature and polarization change causes a signal change in the detector. So this is the functioning of pyroelectric detectors, and they are most suitable in modern IR spectrometers, particularly in FTIR spectrometers. Nowadays we are using deuterated triglycine sulfate. For more advanced detectors we are using deuterated triglycine sulfate doped with alanine. DTGS doped with alanine we are using in most of the modern FTIR spectrometers. Now the third detector is Golay detector. Nowadays we are not using Golay detector. It is the olden detector. It is of obsolete use now. This detector is working based upon the expansion of inert gas in a cell chamber, such as how the inert gas will be expanded in the cell chamber, such as xenon gas. So that is used, and the modified version they are using as photoacoustic detectors, right? They are not using the Golay detector as such. Now coming to bolometer, bolometer is the oldest detector they have used, and bolometer is a temperature sensitive detector connected with Wheatstone bridge, right? Bolometer is basically a temperature sensitive detector connected with Wheatstone bridge, right? So what is the role in bolometer? It is just like a thermometer, and this bolometer, the resistance change in the bolometer is 0.4% per degree centigrade, for if you are using platinum as a material. So what is the main thing? As the temperature of the bolometer increases, its electrical resistance also gets increased. Okay, this is the characteristic thing in bolometer. As the temperature of the bolometer increases, its electrical resistance also gets increased. So the resistance change will be around 0.4% per degree centigrade, right? Now this bolometer, nowadays we are using modern microbolometers we are using. So these modern microbolometers are the best detectors to be used in the far IR region, especially when analyzing the gaseous molecule, right, from 600 to 20 centimeter inverse. The next important detector is thermistors. What is called a thermistor? Thermistor is basically a fused mixture of metal oxides. As the temperature of the thermistor increases, the electrical resistance will get decreased. So it is completely, the function of the thermistor is just opposite to your bolometer, right? The resistance change is 5% per degree centigrade. So therefore you can understand this, the response will be very, very slower with thermistor. So all these detectors are basically the thermal based detectors, right? The last detector what we are going to discuss is photon conductive detectors. The detector response will be very fast, and the classical example for this photon conductive detectors is mercury cadmium telluride. Sometimes we are using indium antimonide, indium gallium arsenide. These materials also can be used here, and they are using under different conditions, because the mercury cadmium telluride, the operating condition is 77 Kelvin cooled with liquid nitrogen. So in this temperature only the detector will be giving a very good response, right? A faster response will be there. Otherwise, if you are not maintaining these operating conditions in a proper manner, you will not get the reliable response in IR spectrometry, right? So this is all about the various detectors in IR spectrometry. Now, concerned with the sample handling procedure in IR spectrometry, gases, we are using the special cell coated with the windows of the special cell is coated with IR transparent materials such as sodium chloride or zinc selenide, right? We are using specifically for gases. Whereas for solids and liquids, we are using some specialized methods we are using. There are 4 methods we are using. One is called residue method. The second one is called melt method. The third one is called mulling method. And the fourth one is called disk method. These are the 4 methods we are using for making the sample for IR spectrometry, especially for solids, semi-solids as well as liquids. What is this residue method? The residue method, what we are doing basically, we take the concentrated solution of the sample and they are dissolved in volatile solvents like ether, chloroform, alcohol we are using, and then you feed dropwise on the rock salt plate, right? Because rock salt is sodium chloride, that is IR transparent material. So you have to feed this on the rock salt plate in a dropwise manner. After some time the solvent evaporates. What will happen? They will leave a thin film of solid as such. So solid residue you will be getting, right? With that you can directly take the IR spectra, right? So this is the preparation of the solid sample called residue method for IR spectrometry, because all the samples are not IR transparent, right? So what we have to do, we have to mix the sample with the IR transparent material, maybe some inorganic salts we are using like sodium chloride or something we are using, and then we are just making the compatible, the material will be compatible as a transparent for IR radiation, then we can directly take the IR spectra, right? So that is the purpose over here, right? The second method is called melt method. What is called melt method? In melt method, we are taking the low melt waxy sample, maybe few milligram of the sample. They are deposited on the rock salt plate and they are heated in oven for melting. Once they are heated in oven for melting, then what we have to do, we have to keep the second rock salt plate over the first, right? That means we have to press these material between the 2 rock salt plates, so that what will happen, it will leave a thin film of sample in the liquid state. So after some time what will happen, it will leave a thin film of sample in the liquid state, right? So this is called melt method, right? The third method is called mulling technique. In mulling technique what we are doing, we are taking 5 milligram of the sample which is grounded in mortar and pestle. We are adding 1 drop of the mulling agent, which is basically nujal oil. The nujal oil is also called as repurified paraffin oil, right? If at all any wavelength of CH bands absorb in the IR region, then instead of this mulling agent, repurified paraffin oil, we have to use some other agents. Maybe we are using perfluorokerosene, or sometimes we are using hexachlorobutadiene, right? So once we use that, then that will give the paste, right? And the paste will be squeezed between the 2 rock salt plates, right? So this is called mulling technique basically, right? Especially it is a semi-solid samples, especially for semi-solid residues we are using this mulling technique as such, right? And the last method what we are using is a disk method. The disk method is basically we are using 2 milligram of the sample. It is also called as potassium bromide pelleting technique, KBR pelleting technique. So the disk method we are using 2 milligram of the sample, mix it with 200 milligram of pure dry potassium bromide, which is of IR spectroscopy grade. And then after adding both these things, we are just trying to ground it in mortar and pestle, and the mixture is loaded in a die. Particularly we are applying a high pressure, maybe around 7 to 10 tons in a pelletizer, so that it will, after some time it will make a die, and that particular sample what you are getting is a solid robust glass like disc. You will be finally getting a disc which is a solid robust glass like disc made up of sample with potassium bromide, right? So that you can directly take it for IR spectrometry, right? So this is how we are using the disk method. Also we are using one more method called diamond anvil method. So diamond anvil method, especially for pressing the hard materials, diamond is very hard, so there also we are using the technique especially for preparing the sample, right? So these are the 5 methods basically we are using for solids, liquids as well as semi-solids. Thank you very much my dear students. Thank you very much.